Hello, my dear students. So, the board exams are just around the corner, right? And I know. This chapter, Haloalkanes and Haloarenes, it can feel a little tough. But hey, don't you worry, not one bit. Your teacher is here to help. Look, there's absolutely no need for any tension, okay? Together, we are going to revise the most important, the most frequently asked topics from this chapter. And I promise you, by the end of this, you're going to have a much stronger grip on everything. You'll feel way more confident about scoring full marks. It's bilkul simple.
Okay, so let's just dive right in. We'll start with Section 1, Naming and Sorting. You know, getting these basics right is the key, Butcho. This is where you'll easily score those 1-mark objective questions.
So, first things first, what are these compounds anyway? It's really straightforward. Just imagine you have a hydrocarbon. You kick out one tiny hydrogen atom, and in its place, you just put a halogen atom. You know, like fluorine, chlorine, bromine, or iodine. That's it. It's just a simple swap. So easy.
All right, now the first important skill you need is sorting them out. We have to be able to tell if a haloalkane is primary, that's the little 1 degree you see, or secondary, or tertiary. And you might ask, sir, why is this so important? Well, because this classification is the secret key to understanding how they're going to react later. It's very important.
So how do we do it? Oh, it's so easy. Just look for the carbon atom that's holding the halogen. Got it? Now just ask that carbon, hey buddy, how many other carbon friends are you attached to? If it says just 1, then it's primary. If it's attached to 2 other carbons, well, that's secondary. And if it's holding on to 3 other carbons, you guessed it, it's tertiary. See? Told you it was simple.
Now, let's quickly talk about naming. So there are common names, like chloroform. You've probably heard that one in old movies, right? But in chemistry, we need to be a bit more professional. We use the IUPAC name. So for chloroform, that would be trichloromethane. For your exam, it's a really good idea to be familiar with both, okay?
Okay, let's move on to Section 2. Now listen carefully. These are the VIP named reactions. I can almost guarantee you one of these is a PUCA exam question. So full attention now, my dear students. Focus.
First up, we have the Finkelstein reaction. Just think of Finkelstein as this super specialist doctor for making alkyl iodides. If you ever need to put an iodine atom onto an alkyl chain, who do you call? You call Dr. Finkelstein.
And here is his special prescription. You take an alkyl halide, you react it with sodium iodide, that's NaI, and, this is the most important part, listen carefully, in dry acetone. You absolutely must write dry acetone in the exam to get those full marks. And your product? Your lovely alkyl iodide.
All right, next up, we have the Swarts reaction. So, if Finkelstein was a specialist for iodine, then Swarts is a super specialist for making alkyl fluorides. You know, making these RF bonds is a bit tricky, so we need a special reaction just for them.
And here is the magic formula. You take an alkyl halide and react it with a metallic fluoride, something like silver fluoride, AgF. Here's a tip for you. The moment you see a metallic fluoride like AgF or Hg2F2 in the question, your brain should immediately scream, Swarts reaction.
Okay, now let's switch gears a little bit. We're moving from those simple chains to the big boss, the benzene ring. So how do we put a chlorine or a bromine on it? For that, we use the powerful Sandmeyer's reaction. The key here, the starting point, is always this very special compound called a diazonium salt.
So here's how it works. You take that diazonium salt and you add the magic ingredient, cuprous chloride, that's CuCl, or cuprous bromide, CuBr. This catalyst is the real hero. It helps to replace that entire big diazonium group with a nice simple Cl or Br.
And our fourth superstar reaction is the Wurtz reaction. This one is actually really simple and kind of fun. Its only job is to take 2 small alkyl halides and just stitch them together to make one big alkane. So what does it do? It basically doubles the number of your carbon atoms.
Here's how the magic happens. You take 2 molecules of an alkyl halide, Rx, you add some sodium metal, and again, remember this, in dry ether. And poof, you get RR, which is an alkane with double the carbons. Just remember that special reagent, sodium in dry ether. All right, brace yourselves for the main event. This is the Bahubali of this chapter. Section 3, SN1 versus SN2. This, my dear students, is a guaranteed 3 or even a 5-mark question. I'm telling you, if you understand this one part, this whole chapter is yours.
So, what is the big difference between these two reactions? How can we tell them apart? Let's get right into this epic showdown, SN1 versus SN2.
Seriously, just memorize this one slide. Think of it as your secret cheat sheet for the exam. On one side, we have SN2. It's a quick, one-step reaction and it prefers primary haloalkanes. On the other side, SN1. It's a slower, two-step reaction that absolutely loves tertiary ones. Did you see that? The reactivity order is completely opposite. Now, don't worry about inversion and racemization for a second, we'll get to that. For now, just take a mental screenshot of this table.
Okay, let's imagine an SN2 reaction. The nucleophile is, well, it's kind of sneaky. It can't attack from the front, right? Because the big halogen atom is blocking the way. So what does it do? It launches a surprise attack from the back. And this backside attack forces all the other groups to flip over, just like an umbrella flips inside out in a strong wind. And that flip, that's what we call inversion.
Now, SN1 is more patient. It plays the long game. It takes 2 steps. In step 1, the halogen just leaves. It packs its bags and goes, forming a flat, positively charged thing called a carbocation. This is the slow step, the important one. Then, in the second, super fast step, the nucleophile can easily attack this flat molecule from the top or from the bottom. And that's why we get 2 different products.
Now, to really get why the products of SN1 and SN2 are different, we have to talk about something called chirality. And the perfect example is right in front of you. Go on, look at your hands. They are mirror images of each other, right? Now try placing your right hand perfectly on top of your left hand, palm to back. Do they match? No way. They are non-superimposable. This property is called chirality, and it's these chiral molecules that give us all these interesting outcomes in our reactions.
Okay, this is it, the final lap. Let's do a super quick, rapid-fire round of some other very important concepts from this chapter before I send you off with my best wishes. Are you ready? Let's go.
Okay, 4 quick points. Number 1, Zaitsev's rule. Just remember this. The richer get richer. The more substituted alkene is always the major product. Easy. Number 2, Grignard reagents, RMGX. The golden rule here is dry ether. Why? Because these guys are super reactive and even one tiny drop of water will destroy them. Got it? Number 3, Haloarenes, the ones with the benzene ring. They are less reactive than the simple chain ones, and it's all because of resonance, which creates a kind of partial double bond. And finally, number 4, please note this down. KCN versus AgCN. KCN will give you cyanides, but AgCN gives you isocyanides. This is a very common place to make a mistake, so don't let it be you.
And that's a wrap. We've covered the most critical, must-know parts of this chapter. Listen to me. You have worked so hard, you are prepared, and you are absolutely going to do great. Believe in yourself. Now go out there and show that exam paper what you're made of. All the very best, my dear students. You've got this.